Now, we've been talking about different types of probability distributions. We're now going to look at this one called the Bernoulli distribution. And it's a very, very simple one. It's actually a discrete probability distribution, but it's very, very simple in that it can only have one of two values. So 1 or 0. Very similar, I guess, to what we saw in logic, which could only be true or false. You see the idea in a lot of computing as well, on and off, that sort of idea. So success or failure, 1 or 0. So if x is our random variable, a Bernoulli random variable, then it has this probability density function. It's simply going to be 1 or 0. They're the only two possible outcomes, and let's say 1 has a probability of p, therefore 0 must have the probability of 1 minus p, because the probabilities have to add up to be 1. But there is another way we could write that then. We could write it like this. We could say the probability that x equals x is actually 1 minus p to the power of 1 minus x and p to the power of x. Because if they're only taking the values of 0 or 1, fine, if you substitute in 1, then 1 minus p to the power of 0, well that's just 1, so we get p to the power of 1, which is p. Substitute in x equals 0 and you get the reverse, so it would cover the whole distribution. So let's draw up a table to work out things like variance and expected value. Now the sum of xpx is p, so the expected value would be p. I guess that kind of makes sense. Probability of it happening. So the variance of x is the expected value of x squared, that's our bottom line there, which is p, minus the expected value of x squared, so minus p squared, which would factorise to be nicely just p times 1 minus p, those two probabilities multiplied together. Now, this is what we know then. If x is a Bernoulli distribution, the only piece of information we really need to know is p, the probability of success. And then we know the expected value will be p, and the variance will be p times 1 minus p. So that now brings up the idea of binomial probability then. And a binomial experiment is when you just continually repeat a Bernoulli trial. So you just do it over and over and again. Now, I start off, there's only two outcomes. I'm just called them A and B. And let's say A is the successful one. It's got a probability P of happening, and B, well, rather than writing 1 minus P down each time, I'll just call it Q. So Q's 1 minus P. Then I'd do it again, and I could get an A followed by an A followed by a B, or I could get a B followed by an A or a B followed by a B, and the probabilities of each of those, well, I'd have P squared, PQ, and Q squared. If I did it again, these would all be the outcomes, and the probabilities would go like that. And do it one more time. Do it for a fourth time, and our probabilities, and we see a familiar pattern starting to emerge. And the pattern really comes out if I'm not actually interested in the order of things happening, just how many times they happen. Because if you look at that, well, when it was just doing it once, okay, probability of A was P, probability of B is 1 minus P, which we're calling Q. When I did it twice, now probability of AA was P squared. But if I'm not worried about the order, all I'm interested in, I get an A and a B. Then that happened in two different ways. I could have AB or BA. And so I've got two lots of PQ. And then BB is Q squared. Do it 3 times. The AAA is P cubed. Again, not worried about the order, but if I end up with 2 A's and a B, I get 3P squared Q. An A and 2 B's, I get 3PQ squared, 3 B's Q cubed. And if we look at the fourth one, then again, here's our pattern. And we recognise these patterns. It's simply the expansion of a binomial. Hence why we call it binomial probability. So if X, we're doing a Bernoulli trial, the probability that X happens exactly K times, so the probability of success K times, will simply be this. The probability of success to the power of K, the number of times it happens, probability of failure then must be to the power of n minus k. But we multiply it by that binomial coefficient, nck, because what we're really saying is how many ways can we arrange those letters? And let's use the 4 events there for an example. Say it was the 3 A's and a B. It's like saying, well, how many different words could I do when I rearrange that? Well, I'd say, well, hang on, it'll be 4 factorial, but divided by the 3 factorial for the repetitions, or another way of saying that is 4c3, so you get the binomial coefficient. Okay. Oh, and of course Q is representing that 1 minus P. Let's have a look at some examples. So in a bag we've got 30 black balls, 20 white balls. We're going to draw out 7. Now, the important thing with this is the probability has to be the same every single time. So it always has to be with replacement. If I don't put the balls back in, the probability will change. What's the probability of getting all black ones? I'll define my random variable, x, to be the number of black balls drawn. That's what I'm interested in here. So I'm saying, what's the probability that x is 7? I get 7 successful attempts here. 7c7, the binomial coefficient goes out the front. Probability of success to the power of 7. Probability of failure would then be to the power of 0. And well, that's an unsimplified answer. If I calculate that out, there it is, 2,187 on 78,125. 4 black ones. Well, now I'm saying, well, 4 successes, that's what I want. X is 4, so probability of success to the power of 4. Probability of failure then would be to the power of 3. 7c4, number of ways I could arrange those outcomes. And there we go, 4,536 on 15,625. And the election. 30% of voters favour party A. Interviewer selects 5 people at random. What's the probability that 3 of them favoured party A? So X is my random variable. I'm interested in finding out the number of people favouring party A. X is equal to 3. I want 3 successful ones. Probability of success, 3/10 to the power of 3. Probability of failure, therefore, is to the power of 2. Put the binomial coefficient out the front, so 5c3, and there we go, there's our answer. Majority favour A. Well, majority would have to be 3, 4 or 5. So I just need to add those 3 possibilities together. And eventually, whoa, there's an unsimplified answer. There it is. 4,077 on 25,000. At most 2 favoured A. All the ideas of probability are still the same. If you think about it, at most 2 is the complementary event to what we just did, majority favouring A. So I can save myself some time there and say, well, that's just going to be the same as 1 minus what we just found. And we get our answer. Let's look at an HSC one. 2005. There are 5 matches each weekend of a football season. Megan takes part in it's a tipping competition. She earns 1 point if she picks more than half of the winning teams for the weekend and 0 points otherwise. The probability that she picks the correct team in any given match, obviously is very good at tipping, 2 out of 3. Show that the probability that she gets 1 point for a given weekend is 0.790, rounded to 4 decimal places there. Okay. So we're interested in seeing the number of matches that she picked correctly. So X is going to be the number of matches picked correctly. We want more than or equal to 3, because to get a point, she has to pick the majority of games, more than half. So 3, 4 or 5. Add those together, plug it in the calculator, and yes, we get 0.7901. Hence, find the probability that she earns 1 point every week of that 18-week season. Now I'm interested in something else. Y is going to be the number of weeks that she gets a point. And so I want when Y is 18. So using the binomial probability idea, I'd say, well, the success is 0.7901 to the power of 18. Therefore, the other one's to the power of 0. Binomial coefficient 18c18, 0.01. I suppose for that one, because it's every game is going to be successful, I could have just simply gone 0.790 to the power of 18. Because every game is going to be the same outcome. Find the probability she earns at most 16 points. At most 16, I think it's going to be quicker to do the complementary, because at most 16, the only other possibilities would be 17 or 18. They're the ones we want to subtract from 1. So we'll subtract those from 1, and we get our answer, 0.92. Here's another one. In a large city, 10% of the population has green eyes. What's the probability that 2 randomly chosen people have green eyes? Well, this is not really a binomial probability to start off with. We're just picking 2 people and they have green eyes. Again, I could have done it with binomial probability and said it's X is the number of people with green eyes. But because each one of them is going to be the same, it's the same as saying 0.1 squared, so we get 0.01. What's the probability that exactly 2 of a group of 20 chosen people have green eyes? Now I've got to use the binomial probability idea. So X is going to be the number of people with green eyes. That's what we want to find. And we want X to equal 2. Probability of success, so it's 0.1 squared. 0.9 therefore is to the power of 18, binomial coefficient out the front, 20C2, all the ways we could arrange that, and we get 0.285. What's the probability that more than 2 of a group of 20, again let's use the complementary event idea, and substituting into all of that, we get 0.32. Alrighty. So 17A, let's play with these Bernoullis and binomial probability.